Greetings, friends, and welcome back to this sequence of my YouTube videos that I hope will be helpful to you as you are beginning your academic journey into the exciting world of electronics technology. We begin today's lesson with series circuits in DC electronics topic number 2. Most beginning students start off learning electronics will be introduced to a lot of theory, such as atomic structure and subatomic particles, such as electrons, and other topics, all of which the theory is very important, and I will be covering the theory as needed in later topic videos. For now, your focus is on hands-on training. Why? Because you learn best by doing, and that's what we're going to do very shortly. Next slide. What is a circuit? We need to define. We use the word circuit a lot in electronics technology. You may have heard circuit used in other disciplines. And we have to define what is a circuit. So a circuit is a connection of some kind of voltage source to one or more electronic devices. Voltage source can be your wall outlet. The voltage source can be a 9-volt battery. Doesn't matter, but as long as we have a voltage source and we have some connecting wires, that will form a circuit. Now, let's see how this is further developed. What is a schematic? A schematic is the visual representation of your circuit that is used in industry as a roadmap of what that circuit is supposed to do and how it can work. It can be as simple as a hand drawing or on a napkin or drawn with electronic software. And what it is you see on the right is one of the schematics that I've drawn for a power supply that our students have built as a benchtop power supply, fun project. So you will see drawings, you'll see schematics such as this on upcoming slides, such as what you've seen on the previous slide that discusses what is a circuit. And this particular schematic goes to show something that was drawn with electronic simulation software. This one is done by a software product called tina.com, tina.com, free online. We'll talk more about software at another time. There's your schematic. Now, this was not drawn with fancy electronic simulation software. This was done with PowerPoint. But it does serve as a really nice visual representation to show what the circuit is supposed to do and how it can work. Now, in electronics, you'll also hear the term that's used a lot called a load. What is a load? A load is an electronic device, such as a lamp, a fan, or motor, or any of a number of things, speaker, buzzer, that can be connected to a circuit. Some interesting examples, let's go back. Some interesting examples of loads are visually shown here as a fan, a lamp, and some kind of a loudspeaker. Now, basic electronic circuit, the most basic circuit consists of a minimum of these things. You must have a voltage source. I'm using a 9-volt battery in this particular case. You must have connecting wires, and then you have a load. So these are the elements that make up a basic circuit. And so you can see I've got a DC lamp here, and I'm hooked up the terminals of a 9-volt battery, the plus and the minus, with connecting wires to the appropriate connecting points on the lamp. And if everything is connected properly, it should light up. So this is a basic circuit. Remember now pay attention, a voltage source, connecting wires, and a load. That's your basic circuit. Now, the circuit can be on or it can be off. So if we discussed previous lesson, the lesson was on continuity. And so if we have no continuity, no continuous path for electricity to flow, Then the circuit is defined as being off. Circuit is off as illustrated in the left-hand illustration. So what we have here is our same 9-volt battery, same connecting wires, and a load. This does form a circuit. However, this circuit is off, and the reason why it's off is because we have no continuity. There's a switch here that has been pulled up, so no contact is made. There is no complete path for electricity to flow. This switch is called an open switch. And as this is an open switch, as there is no continuity between the lamp and the terminals of your battery, no electricity will flow, and therefore the lamp is off. If we look at the illustration on the right, continuity in this particular case shows that the circuit is on. And what we have here is the switch is now closed. So with a closed switch, we can see that this has come down to make contact, and we now have a complete, we now have a complete path for the electricity to flow from the terminals of the battery to the appropriate contact points of your DC lamp. And so electricity can flow now because we have continuity and the lamp is on. Now, basic types of circuits. You have what's known as series circuits, parallel circuits, and something called series parallel circuits. Series circuits are defined as those having only one path for electricity to flow. If you look at the corresponding illustration on the right, you will see a 12-volt DC voltage source. And I'll get into the details of what is DC versus AC in a later discussion, later topic video. But this is defined as a DC voltage source, and it could be a battery, like your car battery. And I happen to have 3 loads that are attached. These happen to be resistors. These are the illustrations for resistors, which is a very common electronic device. And in schematic drawings, it illustrates that I have 3 loads attached to a voltage source. The voltage source, the DC voltage source, is shown as having short and long plates. These would be plates similar to the plates you have in your car battery. And the short plate is the source of your electrons, the source of your electricity that flows around this circuit. And as you can see, if the electrons flow from this negative plate, follow the wire, it can only go in one path through 3 resistors that are in series. We call them series resistors because they are arranged in a series circuit, and the current flows back to the positive side of the voltage source. One path means series circuit. A parallel circuit would be defined as one that has multiple paths for electricity to flow. If you look at my illustration on the right, you'll see the same DC voltage source. You'll see the positive plate, which is the long plate on top, negative plate, short plate on the bottom, and electrons are said to flow from the negative plate down to the right. And as soon as it hits this dot, we call this dot a node. A node is a connection point in schematics, as well as a connection point on your boards when you build things. And at this particular node, the current will split. Part of this will be divided to come up through this load resistor, and part of this will continue on this wire to the other ones. When the current comes here to this next node, you can see that it can be split again. Part of the current will come up through this load resistor, and the rest of it will come over to this load resistor. What will happen to the electrons then is as they flow through the resistors, the electrons will flow through the 3rd resistor on the far right into this node, the electricity flowing up from below on the 2nd resistor will combine, and they will flow through this wire to combine with the current in the 1st resistor, and all total coming back to your DC voltage source. So the amount of current that leaves the DC voltage source is divided between the multiple paths and will recombine at the top to be the same amount of current coming back to the DC voltage source. A third beginner circuit that you're introduced to is called series parallel. And series parallel circuit is shown where parts of the circuit may be in series, other parts may be in parallel. And if we take a look at this illustration here, again, our DC voltage source, positive plate on top. In this, as is shown here, negative plate happens to be on the bottom. Electrons leave here, come down, and flow through this first resistor. This first resistor is in series with the voltage source, meaning there's only one path between the voltage source and this resistor. So this resistor is in series with the voltage source. Once the electricity flows past this resistor and hits this first node, and as you can see, it will be divided and split into four paths through these four resistors, and the electricity will flow through these resistors to recombine at the top, and the electricity will then flow through the top resistor back to the voltage source. Now, I've used some words here that might be misleading from the standpoint that electricity doesn't quite flow the same way as current in a river and tributaries flows. In other words, the amount of pressure of flow, electron flow down here in the bottom part of the circuit is equal in amount and also simultaneous to the amount of current coming back at the top. It is instantaneous in all parts of the circuit. There is no bunching of current that happens here and then lesser current in each of the branches and then recombines at the top, much the same way that water does in a river system. Here, electrons flow at the same time all around. So as an electron leaves the negative plate, an electron will come back to the positive plate, and this happens instantaneously. More about that later. So these are the three basic types of introductory circuits that you're introduced to. We're going to focus our attention today on series circuits, one that has only one path for electricity to flow. Here is your first series circuit. And the series circuit is shown in two illustrations. If you look at the upper left, it shows the DC power supply on your breadboard and some jumper wires, an LED, a resistor, and another jumper wire. So here, the description reads, the DC power supply switch is off. And the switch is this little push button right here. It's off, so there is no continuity. There is no energizing of these power rails by the power supply. So as this is off, there is no continuity of these rails to the power supply. The LED, which is your light emitting diode, that's what LED stands for, is therefore off. If we take a look at the lower right illustration, you will see that the board is now energized because the board has an LED of its own that will show that it is in the on position. It's turned on by virtue of you pressing down this latching switch. Once you press down once, this will light up and electricity will be allowed to flow through these power rails in the circuit that I've built and that you will be building in just a moment to show, well, we have continuity of these power rails with the power supply, therefore, and the power supply is on, and therefore the circuit is on, the LED light emitting diode is now on, and you can see the contrast between an off LED up here in the upper left illustration and the on LED as it glows in the lower right illustration. Next, we will talk about what to do in order for you to build your first circuit. So what you got to do is from your project kit, very carefully, why carefully? Carefully so as not to accidentally spill out the contents. I've had some students have some accidents in the labs. They were not as careful as they ought to be, and the contents all spilled out onto the floor. And they're crying the big tear because picking up these hundreds of little components off your floor is very tedious indeed. So very carefully pull out the following pieces: your breadboard, your DC power supply, your USB-A cable, which is a blue colored cable. I'll show you that in detail in a moment. any color LED of your choice, a 100 ohm and a 1K ohm. Now, this is a symbol for ohm. This is the Greek letter omega, and it represents the unit for resistance, and 100 ohms is a certain amount of resistance. 1K is 1,000 ohms. So you pull out one of each of these. Only pull out the 100 ohm initially, one resistor at a time. I'll tell you why later. Then also a short red and a short black jumper wire. Now, you may be supplied a kit from your college, university. If you are not supplied a kit or have not purchased one already, this is one that has worked out very successfully with my students for many years. And the link to this is available to Amazon as an affiliate link at the end of the YouTube. Now let's get further into pulling these things out and what they're going to look like. This is what they're going to look like. There's your short jumper wires, stainless steel pins on either end, one red, one black. There is your LED, and notice the LED, you choose whatever color you prefer, but notice one wire is long and one wire is shorter. That has a great deal to do with how you go to put it onto your breadboard. Then we have a single 100 ohm resistor. There's your 100 with the omega symbol right there. Only pull out one of these. And then your USB-A cable, which will be connected to your power supply on one end, and the other end connected to your laptop or some other type of power supply, as we illustrated previously. And why only one resistor? Well, you'll find out why in a moment. So let's go ahead and begin with your power supply. So here is your DC power supply that's supplied with your project kit. What's nice about this is it allows you to do experiments at home. You don't have to always be in the laboratory as you begin your studies in DC electronics. This is a very nifty breadboard power supply. It is a regulated DC power supply, which means it'll supply very stable amount of voltage and current to your electronic projects. Now, this has to be set up very carefully. The illustration on the left shows these jumper pins removed off of the pins on this left side and the jumper removed off of the pins on the right side. We have to set this up properly for our use. This allows us to select between 5 volts or 3.3 volts on either side or switch it into the off position. Do nothing with these jumpers that are here. So what we're going to do is these are easily removable by hand, and we're going to place them into these pins shown in the illustration on the right. Here, we put the jumper connecting the far left 2 pins between 5 volt and the off pin. So 2 pins are now joined with a jumper on the left side of your power supply board. And on the right side, you want to take that jumper pin and connect it to the 2 center pins for off. We want this to supply no voltage whatsoever to your lower power rails. Okay, so this is how we will begin. And I will show you how to do that in just a heartbeat. So here's a close-up of the DC power supply as it comes out of your project kit, and it has some jumpers in place. Wherever the jumpers happen to be in place, you just go ahead and grab them and carefully pull them off the board, off the pins. They will grab and slide off, one like so, and one like so. And as we've indicated, you want to set this up in such a way that on the right side of the board, as shown in the illustration, we want to connect between the far left pin and the pin next to it so that we are supplying 5 volts on this side of the power supply to the rails of your breadboard. And the power rails of the breadboard will be corresponding to, say, something that looks like this. So the +5 will be connected to the red rail. The off, which is the ground part of the power supply, will be connected to the blue rail. Okay. Okay. So let's go ahead and pop one of these jumpers back on right now. I'll take this and do this and push in place, like that. Okay. The other side, I'm going to recommend for now, not using 5 volts or 3.3, but connecting the jumper between the two middle pins, which will turn off any kind of power from this side whatsoever. So I'm going to go ahead and do that now. Take this and align, look carefully, and push down firmly like that. Now it's in place. This power supply is now ready to go onto your board. Now, what we're going to need to do next is to make sure it goes onto the board very carefully. And that's shown in the next slide, but since I have the camera on, let me just show this to you now. We happen to have on the underside of the board, as you can see, 4 pins on one side, another 4 pins on the other side. That means we have a total of 8 pins that have to be aligned very carefully. Now, if you look at this, you can see most of these are nicely parallel. This one here on the forward right-hand side may be a little bit tilted, but you know, if it is just a tiny bit, I'm going to give it a little bit of encouragement to try to straighten that out just a tiny bit. Don't break these pins. Last thing you want to do is injure this board in any way, shape, or form. What we're going to do is now we're going to attach this to a breadboard, and I'm going to recommend, for the sake of consistency, that we set up our breadboards with the red stripe, the red power rail, away from you at the top of this illustration, because what we're going to do with our power supply is, since we've already set this up to be 5 volts, you can see that I have the plus and the minus terminal of these first 2 pins that will be connected to the positive rail and the negative rail. Now, the most secure place to mount this will be in the very first set of points right here. They align very nicely with your power supply. So just very carefully align this way, and very carefully align the other side. Very gently, what you're going to be doing is pushing down. And what it is that we have, once it's put down in place, it'll look like this. So I'm going to gently pull this guy off. There's your 8 pins right there. And I have to go into the power supply onto the board. I'm going to carefully line things up like so, like so. It may take a little bit of patience and doing back and forth. You're going to need to look at these pins very closely and confirm that, yes, they are about ready to be pushed down in. Don't press down until all 8 pins are correctly into their corresponding holes, all right? Because the last thing you want to do is to press down and actually damage any of the pins. Once you have the confidence that the 4 pins on the 5-volt side and the 4 pins on the off side are properly positioned, then and only then push this down firmly, and you can see that is the end result. Okay, let's give this a moment to focus. Having a challenge because I've got this really, really close up. But yes, you can see no gap here and no gap here, and it's hanging very, very nicely. Let me pull the camera up just a little bit. There, now you can see it's very nicely on the board with just a little bit of overhang here. That's fine. So we do want the red rail on the top. This will be the power rail that will be supplied by the 5-volt source. And we will be connecting to these 2 rails. For convenience purposes, as the circuits continue to be more sophisticated, we can also use this blue rail here as a connection to completing our circuit. This blue rail and this blue rail are continuous with each other through the board, but there is no voltage that is supplied to this red rail. The voltage is only supplied through this upper red rail, but we can return our current through either this blue rail or this blue rail. More about that in a bit. So let's go ahead and pause for a moment. Okay, hopefully we're able to see the slide that shows attaching the DC power supply. And so to reiterate, with the upper left illustration, says carefully align all 4 pins onto the red-blue rails at the top. Carefully align all 4 pins to the red-blue rails on the bottom. In this fashion, a little bit of overhang is correct. You want to make sure that these are aligned carefully so that no pins are crooked, that all 8 pins are definitely going to go into little pinholes. And only when everything is straight, ready to go in firmly, only when all 8 pins of the board are aligned correctly, then and only then, press firmly down onto the board with the power supply, and you can see that this is now seated as I've illustrated for you in the video a moment ago. Now, how can we supply energy to the board? We can supply energy to the board in this fashion. Let me go ahead and click on this and here. All right, we can supply electricity to the power supply board by a number of different means. As I've said before, that this USB-A to USB-A connecting cable is nice and short, allows you to hook up your power supply here on your desktop and on the other side to your laptop, which is the most commonly used device for powering your board. But you can also use a cell phone charger. And what's nice about using a cell phone charger is that this makes it quite a bit more portable. And because of the short length of the cable, may be more convenient for you to have the breadboard set up in a more convenient place on your desktop, and as opposed to being right next to your laptop, things may get crowded. I do caution you this: if you are going to use a cell phone charger, then this will energize your circuit for just a few seconds, just to allow you to do the testing to confirm that things are working. If you want to leave your circuit running for further testing for any prolonged period of time, the cell phone charger is not going to do it for you. You really ought to plug this other end into, say, a wall wart of some sort. What do I mean by wall wart? I'll show you that in a moment. Or directly to another power source. Now, next one. Let's go ahead, show you here. Okay. As your circuit will be built shortly, okay, what we're going to do is, before we go to build this, let me talk to you about how to pull stuff, the rest of the stuff, out of your case. So let me go ahead and do this for just a moment. So I wanted to take a moment and talk to you about how to pull things in and out of your project box. Your project box, such as this particular one, happens to have 2 latches, like so. Help to prevent this from accidentally opening up and spilling out all the contents. And as I've said, if all these contents spill out, you will be crying the big tear, picking up the hundreds of individual little pieces off the floor. As we go to open this up, you can see I've already removed the breadboard and the power supply. And here you will find your packets of resistors. We use these resistors as loads for our experimentation. There are other loads that we can use, but the resistors are the most common ones, and they're marked with individual values as to the amount of resistance, the amount of ohms they represent, and they're marked very clearly. We'll set these aside for just a moment. Your LEDs are shown here, and then other devices, if we very carefully pull those guys out, what it is that you have is a nice set of pre-cut, pre-bent jumper wires There's your pre-cut, pre-bent jumper wires. We'll show you on a separate topic video how to use these properly, and you'll find these to be of tremendous help to you in making your circuit builds nice and clean. We'll leave these at the bottom of the case for the time being in the back. Make sure this is capped. This is the last one that you ever want to have pop open, because there are literally many dozens of pieces, and to have this fall on the floor, you will definitely be crying the big tear. I do recommend, perhaps even for security purposes, just putting a nice rubber band around this so that this doesn't accidentally pop open. We'll just leave this into the bottom back of your case. And what we'll do next is, these are your variety of jumper wires. These are set up as male to male. They come in different lengths. No need, absolutely no need to keep this with you in your backpack, in your case, all the time. You only need a few of these for your labs at school, and you only need to use a few of these for any experiments we'll be building. They give you way more enough such that this one bundle will probably supply the needs of your entire class. Unless you're building really complex projects. We're going to set this aside, okay? Not have to carry that with us. You're given extra sets of project jumper pins, which we will talk about at a later date. You can set that aside as well. You are also given a strip which you can peel off one at a time as you need. And these jumper wires have female on one end and have male on the other end. Again, very useful. We're not going to be engaging with those today. We'll set those aside. Now, so what are you going to keep with you? Oh, yes, you have these black cylinder devices. These are your capacitors. We're not using these now. You can also set that aside, leave those at home. This other case happens to have transistors and some chips, some speakers, and some variable resistors. We're not using these right now. Also, you can set those aside. The LEDs and the resistors are what we will be using initially. So as you go to build your circuits at home, and I highly recommend you pre-build your circuits at home, because building circuits can be very time consuming, and you don't want to waste time in school building your circuits because you want to use your school time for actually making the measurements, comparing with your instructor, certain things that are working properly, certain things that are not working properly. So you want to take time and build these carefully at home. Once you build these carefully at home, then you now have the rest of this space in your project kit to be able to store your projects without losing the pieces. So what I highly recommend for you is, we're going to pull these guys out. I do recommend that you get a pair of needle nose pliers, spring-loaded so that it can be like so. All right, you squeeze to hold and let go. And these will be very handy, and I'll show you why in a little while. But these will go down here at the very bottom. All right, your breadboard is designed such that it will go, let me go ahead and take this, put this on this side. You don't need electrician's needle nose pliers. I mean, something that your grandfather used for electrical work is way too big for this. So some small needle nose pliers with spring load can be found at your friendly neighborhood Harbor Freight or Walmart. Then your electronic board will go down like so. And you can see, even with the power supply in place, the board fits in here nicely. And if your board happens to have a bunch of components built on it like so, and I'll just go ahead and attach another power supply onto this board. Okay, it can sit very nicely in here with, and you can still close this without crushing your components. So what is it that you need in school will be your jumper wires, your LEDs, your resistor packs. Okay, and arrange those so that they go up there like so. And then a few, not many, a few of these handy dandy jumper wires. You don't need to bring in the entire bundle, okay, because that's way too much to bring. So a few of these sprinkled in here will be just fine. So I'm going to, for example, just go ahead and pull a few of these out and sprinkle a few down there. 6 or 8 should be more than enough. And then your project board or boards can go in place like so. and you have enough room to be able to do multiple project boards. And this closes up nicely like so. This latches like so. And I highly, highly recommend you use a stout rubber band around the outside so that when you have this in your backpack, you have this in your other toolkit, whatever you may be using to carry, should these latches accidentally come loose, you don't want this lid flipping up and having all the contents spill out, because why? You don't want to be crying the big tear. Okay, so latch, rubber band, and that's how you'll be pulling devices out of your kit. Now, once that's said and done, how do we pull out your resistors so that they have the best opportunity to work properly on your behalf? So your resistor packs come marked with the amount of ohms. The omega symbol is the amount of ohms, and they are attached in this way. The most common challenge that people have with students have with respect to the resistors is very simply this. If I go to, let me pick the one that's correct. 220, 220, 330, 20K, 10K. Okay, here's 100 ohm. I said we were going to use two resistors, but we're only going to do one resistor at a time. And these are the loads that we build into our circuits for our initial understanding of electronics. So this comes out of your kit like so, and is fastened with masking tape at the top, fastened with masking tape at the bottom. And one of the hazards is don't pull out multiple sets at the same time. You only pull out one set of resistors out of one pack at a time. Why? They look very similar to each other, okay? And if you get them mixed up, it'll be harder to know which will go into which envelope, which will go into which plastic baggie correctly until you learn how to read the color coding that's on here. The color coding we'll talk about in a separate topic video, but for the time being, if you only pull this out one set of resistors from one pouch at a time, we are gold. So what you do here is, as these resistors are fastened with masking tape on either side, you want to very carefully hold the tape with one hand, very carefully pull out one end to free that, like so. Then, very carefully on the other end, hold the masking tape and pull this out. All right. Now, the most common issue students have is there may be some masking tape residue still stuck onto the end of the resistor wires. The last thing you want to do is to have that adhesive go down into your breadboard and gumming up your pinholes. So I highly recommend that your hands are clean, your hands are dry, and you can just very simply do this. Just remove any type of residue that's there. If you are blessed with particularly sweaty palms, as some of my friends are, you might want to just use a handy little towel and very carefully make sure that the ends are going to be clean. That way, when you go to build your resistors onto your project board, you will at least have the assurance that no gummy residue is left on the tip of the wire from the masking tape as it goes into the board. Okay, so we pull out a 100 ohm resistor, we set it aside, and then we'll pull out the rest of the devices. You are also going to pull out some color LED of your choice very carefully here as well. Hold this, open up the latch, open up the lock carefully. Now do this on your table, not out over the open space, so that if something were to happen and this were to spill, at least it spills very, very close onto your table and not all over the floor. Just pick an LED of your choice, close this, and make sure it's all secure. Nothing is binding the closure. And lock and latch this, and that's ready to go back into your kit for the time being. We have an LED of choice. The LED, if you look very closely, happens to have two wires. One wire is longer than the other wire. The longer wire is connected to the positive side of your circuit, meaning the red rail side. And then the shorter wire is to be connected to your negative side of your circuit, or the blue rail side, all right? And so please note that as your LEDs come out of the kit, they are all going to have one longer lead and one shorter lead to help you identify which way the LED goes. Okay, let's go ahead and talk about the next thing. Here we go. Okay, we will be doing this together, step by step, but I wanted to give you a preview of the step by step on a screen before we go to do this with our own hands. So what you're going to do is, with your breadboard DC power supply off, you want to make sure this is not energized, this LED is off, and you want to connect, number one, the red jumper wire from pin 30A. So this is pin 30, and these are arranged A, B, C, D, E, F, G, H, I, J, K. So 30A is this very first hole right here. So one end of the red jumper wire goes here, the other end anywhere on the red rail. You take your LED, and the LED's long pin will go into row 30 as well, or column 30 as well. And it will be specifically in row C, 2 pins away from your jumper wire. And then the other side of this will be, of the LED, the short wire will be on 32C. And then the black jumper wire will be connected from 32E. This is very much like bingo, as you have the coordinates are a number and a letter. So here we have the black jumper wire on 32E, and this will then connect to any point on the blue power rail. So right now, the circuit will be built, and circuit is off. And when we go to press the button, just for a moment, don't leave it on indefinitely, because this LED can burn out under these circumstances if left on for anything longer than just noticing that the circuit works. So we then will be energizing the circuit to confirm that everything is working. So what I'm going to do with you at this point is do this with you manually. Okay, so as we go to do this together, I now have the breadboard in front of us. It is empty of components except for the power supply. Power supply actually is not even connected to power right now. We don't need it just yet. Make sure that this is properly in place as we've illustrated and demonstrated earlier. Once your power supply is on the board, no need to remove it. You can store it in your travel case just fine with the power supply board on your breadboard. Our first connection is to take our red jumper wire, and we're going to connect one end into 30A. So if you notice right here, you happen to have the letters A, B, C, D, E, and then F, G, H, I, J. And so these rows correspond horizontally, and then we have columns that come down this way. So if I want 30A, like bingo, here's 30, and here is row A. Well, 30A is this hole right here. The next hole of interest for us, the next pinhole, will be 30C. 30C is where our LED long lead will go. 32, we'll count 2 places. Here's 31, 32. Here's 32C. 32C is where the short wire of the LED will go. And then 32E, pardon me, is this pinhole here. This is where the black wire, black jumper wire is going to go, and the other end of the black jumper wire anywhere on the blue rail. So without further ado, red wire on 30A. There it goes. Now let's bring this right down so you can see as clearly as I can make it for you. There is 30 on row A. And then the red jumper wire anywhere on the red rail. Makes no difference. Okay, done. Then you're going to take your LED. I said any color LED. I happen to have grabbed the red one in this particular case. And you have a long wire and you have a short wire, and you want to splay these apart just a little bit. So the long wire will go into 32, excuse me, 30C, which is this one right here. All right. And then the short wire will come two spaces over and go to 32C. So what this will end up looking like, I'm going to come in from this angle so you can see a little better. Like so, long wire goes in first, this is longer, and the short wire like so. And therefore, we now have the red LED into the long lead into 30C and the short lead into 32C. You want to seat that, push it down, okay, firmly, not too, don't crush it onto the board. It's okay that there's some space that it stands up. Okay, then we're going to take the black wire, and the black wire's got to go to 32E. So here's row E over here, and 32 puts us right there to line up with pin 32C of the LED. And we'll go here, push down, and then the other end of the black wire anywhere on the blue rail, like so. Okay, so there's your circuit build, your very first circuit build, and we're now going to see if this guy is going to work properly for us. Because of convenience purposes, I'm going to do this just to show that your cell phone charger will only work for a brief period of time. I'll bring the camera back up just a bit. Go here, and let's go ahead and connect one end of the USB cable there, and the other end of the USB cable. So this one goes this way, okay. And now press this guy. The board is now, power supply board is on, the red LED is lit. And if I just leave this for a bit, you'll notice that this may fade out and actually turn off because although this is wonderful for charging your cell phone, it doesn't last forever on your circuit board in this fashion. So we'll turn that off. If I do, however, wish to have this on for study purposes, I will use a wall wart. Here's your cell phone wall wart. This works really well because on one end you're connecting this to a wall outlet, and on the other end you may have one or two USB ports for this. So by connecting here, which I'm doing with an extension cord here, just because I have extra length here, I now press this, and this guy lights up very nicely, like so, and works beautifully. Let's go ahead and change this to maybe a different color. Pop this in here, pop that in there, and they're nicely lit. It's bright, it works. Just confirm that it works, power it off. That's what you're going to do, and hopefully yours will look like this and is complete. Just remember, as soon as you confirm that the LED is on, your life is good. All right. Now, a very helpful comment from a colleague of ours. This was suggested on the YouTube comments, and I highly value your YouTube comments from a colleague down under. Down under is Australia area, the other side of the world from where we are in Nevada, Las Vegas. So the comment was, sometimes these boards don't work the way that they're supposed to because they're budget boards. The kit is a budget project and kit, and sometimes they're just a little fussy. Why? Because of a number of reasons. Other reasons, many reasons could be that these spring clips that I showed you before in the previous topic 1 video may have some residue in them from the manufacturing facility, maybe a slight film of some kind of something that prevents good electrical contact from the wires of your LED or other devices that are shoved into the connecting points, and therefore things may not work out as you hope that they do. Yes, the continuity pattern is supposed to be like this, and we're supposed to be able to rely on power rails working consistently, and we're hoping that the tie points part of our breadboard works consistently. If, however, that doesn't happen, a number of reasons. One of the most common reasons is some kind of sticky residue that may be on the ends of your components, especially the resistors, since they come off of masking tape like so. So we said you want to clean the ends of your resistor wires. The other reason could be that the tie points themselves, these points, may be a little fussy. And if they are, we're going to do something called frogging. What is frogging? Frogging is like your frog leapfrog. It'll jump from one to another to another. So if, for example, I go to hook this up and I light this up and the LED does not light up, well, it could be a variety of reasons. The most common reason is that the LED is backwards. So if I take this and I flip this guy around, and you can do this in your sweet time as well, very interesting. If you go to do this, and flip it around so that the long lead is facing the wrong way. Push this down. I'm pressing the button. And as I press the button, see, watch, the LED to the power supply board is off, means my switch is off. If I press the button, this LED is on, which tells you the power supply is working, but there is no continuity in the circuit because the LED is backwards. If, however, I leave that on and I take the LED and I flip it around the way it's supposed to be connected, long lead on pin 30, C, and the short lead on, watch, boom, it lights up beautifully, okay? So that's one reason why the circuit may not be lit up. Another reason why the circuit may not be lit up, separate of residue or some kind of contaminant on the wires, there could be some contaminants onto the breadboard. Now, if you happen to run into one or two of those, doesn't mean you've got a bad breadboard. It simply means that you've got to use your breadboard more often. So the continual pulling up and down of these pins into various holes will ensure better electrical contact to your circuit. So if, for example, I happen to have this on the blue rail and it does not light up, it lights up in this case, but let's say for a moment it doesn't light up, it simply means that that particular contact point may have some contaminant in it. So what am I doing? I am frogging my wire and simply taking the end and moving it to another location that should ensure me the same result, even though the one right next to it may be fussy. All right, so that's a technique known as frogging. So I thank my colleague from Down Under for pointing out that there may be some inconsistencies with the breadboards because of their budget, or also because of some possible factory contaminants that may have lodged into any of these pinholes. Turn this guy off when we're done, and let's go ahead and do the next test. We got to put in the 100 ohm resistor, and that can be a little tricky. So now we're going to add the 100 ohm resistor that we've pulled out of our kit. And for the time being, we won't talk about the color coding that identifies it at 100 ohms, nor will we talk about how to measure with your multimeter that this is 100 ohms. Those are part of a separate topic video. For the time being, as long as you have read the label of the plastic pouch carefully, that it shows 100 with the omega symbol, life is good. You've pulled it out of the masking tape ends, you've cleaned the ends, and now what we're going to do is take one end of that resistor and place it into pin 32. This will be pin 32C. I believe. What do I have here? Red jumper into pin 30A, the other end to the red rail. Connect long wire LED to 30C, the other end to 32C. Black jumper wire. Oh, okay. I've got to change the wording on this. So let me go ahead and fix that for just a moment. Copy and paste. All right, that's updated correctly now. So as we look at the slide that shows add 100 ohm resistor, it shows we're going to take the red jumper cable as we've done before, hook one end to 30A and the other end anywhere on the red rail. We're going to take the long wire of your LED and connect the long wire into pin 32C, 30C, and then the other end to 32C. The short wire goes to 32C. And then jump down 1 to 32E is where one end of your resistor will be connected. So resistor to 32 D, excuse me, to 32D right there, and then jump it on over to 40D. So the resistor one end will be connected to from 32D, the other end jumping over to 40D. And if we jump down just one more pin to 40E is where your black jumper cable will be connected, and then the other end back to any point on the blue rail. And if all goes well, then what it is you will see is this device will light up. And let's go ahead and see how we go to do that. What we're going to do is put this on pause for just a moment, get the hardware set up again. Okay, now the hands-on part that will match our slideshow. So this is the circuit as we've set up before. Jumper wire, single LED, jumper wire, and everything worked very nicely, like so. Power on the power supply board and power on the LED. Now, we don't want to leave this on for an indefinite period of time because that LED will burn out. So this is only for a quick test to know that the circuit is working. So what we're going to do is we're going to take this guy, pull it over to 40E, and that will leave a gap. The gap shows we have no continuity between the short pin of the LED to the black jumper wire. What we're going to do is we're going to fill in this gap with our resistor. So here's your resistor. The resistor has very fine leads. This is a precision resistor as identified by 5 color bands. I'll differentiate precision versus non-precision resistors in a separate topic video. And this is what we call an 1/8 watt resistor, meaning that it has to do with how much heat this guy will dissipate in comparison to physically larger resistors such as this, which can be 1/4 watt or 1/2 watt resistors, meaning they can dissipate quite a bit more heat. So the physical size of the carbon resistors that we're using is indicative of how much heat they can dissipate safely before they burn out. So one of the things that you'll notice is the wire of the resistors we're using is fairly thin. In comparison to the larger wattage resistors, they have much thicker, more stout wires. So when we're going to put our resistors, for the time being, on the board, what we're going to do is we're going to grab the resistor, give it a slight bend like so, slight bend like so, and then a slight bend like so, okay? And therefore, we have created something that looks like the letter C, or the letter U, or the letter N, doesn't matter, just messing with you. Okay, so what we're going to do very carefully is grab one wire, the wire that we're going to insert, move the resist LED out of the way. Our target is to hit 32D. So grabbing the wire very close to the base will ensure us not crumpling this wire, because if we hold this at the resistor, and if we hold this at the body of the resistor like so, and we go to push this down onto a breadboard, okay, what can happen is this wire is so thin it can crumple. And the most frustrating thing is to work with resistors with crumpled wires because they're hard to uncrumple. So two ways to be able to avoid this. One way is to hold the wire as close to the end as possible. So it's very short amount of wire exposed. Very carefully position this into the hole that you want. And perhaps maybe the LED's in the way, maybe this is in the way. This may give you a better view. So we're going to position this into 32D. Right there is 32D. Once I have it aligned to the hole, I will very carefully push straight down. Just a minor amount of force. I'm going to take the other end and align it to 40E, and very carefully, again, grabbing the wire near the end, push it down firmly, and that's it. You don't have to crush the resistor onto the board. in order to make contact. Now, if you find your pinholes to be very, very tight because your wire sockets are brand new and the spring might be very, very taut, then I recommend that you, if it's very, very taut and you can't push this down very carefully, hence comes your needle nose pliers. And the needle nose pliers are very handy. And notice I'm grabbing this from an underhand position and spring loaded so that I can squeeze to grip. And once I let go, the jaw is open. So what happens in this particular case is I can grab the resistor and very carefully like so, very near the end of the wire, guide it into the specific tie point of interest and push just a little bit, and then push a little bit, push a little bit, push a little bit. And by gently pushing a little bit this way, it will give you a nice connection with the least amount of crumpling of the wire. Now, you'll find this not to be the case when you graduate your resistor collection to the slightly larger wires. They have larger resistor wattage dissipating resistors, and the wires are quite a bit more stout. But for these being very fine, you might use one of the two techniques that I showed you. All right, so let's go ahead and rebuild this since I took the LED out for visual purposes. Almost all, there we go. Take this guy, put this guy, long lead here, short lead there. Resistors back in place, red jumper wire is back in place. All right, so if everything works as I hope it does, and for the sake of this video, please work. Whoop, it lights up, yay. Power supply board lights up and the LED lights up. And in this particular case, if we do all our calculations, and I'll show you calculations in a separate video, if we do our calculations properly, this resistor, as it is here, restricts the amount of electricity that can flow. Resistor resists. And I try never to use the word to define itself. So the resistor's job is to oppose the flow of electricity to a certain degree. So the amount of resistance can vary depending upon the design of the resistor. So 100 ohms has some opposition to current. It will restrict the current to be a certain amount depending upon other devices that are in the circuit. And used in this fashion, this is called, because of its function, a current limiting resistor. One resistor, in addition to an LED set up this way, is for the purposes of protecting that LED so it doesn't burn out because of excessive electricity without the resistor. Without the resistor, if I go to connect this, ooh, it's quite a bit brighter. You might not notice it's straight on, but that's quite a bit brighter. And then if I do this here with the resistor, it's not as bright. So this is with the resistor, and this is without the resistor. I'm bypassing the resistor. And you can see it's quite a bit brighter. And for those of you who want an even better view, let me just bring this puppy right down. And with the resistor, I'm connecting the black jumper wire to the end of the resistor, so it's now in series. You can see I've got that amount of illumination. If I bypass the resistor and come straight up to the LED pin right here, boom, quite a bit brighter. So the job of the resistor is demonstrated by it limiting the amount of current that flows through that LED to protect it. We still have enough of an illumination from the LED to show that, yeah, it's on, circuit's working. We don't need the LED super bright as here because we can burn out the LED. So the resistor is doing its intended job, and that is to resist the amount of current flowing through the circuit to a very limited amount of current. We'll talk about what current is in a theory video coming up shortly. So what we're going to do next in our PowerPoint slideshow is we're going to change the 100 ohm resistor to a 1 kilo. K stands for kilo, and kilo means 1,000. So we're going to change this from 100 ohms to 1,000 ohms, meaning 10 times the amount of resistance. What do you think? If I grab a hold of that garden hose that you're using to wash your car, and you have it on nicely washing the car with a nice flow from the your faucet, and if I go to grab a hold of that hose and squeeze it, am I presenting more resistance to your water hose by squeezing the hose itself? And shouldn't I have less flow of water through your garden hose if I squeeze the hose itself? Well, changing the resistor from 100 ohms to 1,000 ohms is very much like squeezing that garden hose. I am going to restrict, or you will be demonstrating to yourself in a moment, that we're going to introduce a higher amount of resistance, a higher amount of restriction to current flow. And what should happen as a consequence is that the LED is even dimmer, okay? It should be even less bright with a 1,000 ohm resistor than with a 100 ohm resistor. So before we go to change that out, I'm going to show you some handy steps to avoid some confusion with respect to your resistors. So you may recall, I did say much earlier, only pull out one resistor, only pull out the 100 ohm resistor. Even though we're going to use a 1K, the 1,000 ohm resistor in a moment, only pull out one. And the reason for that is you want to make sure, because until you learn how to measure the resistance of these with your meter, as well as until you learn how to read the color coding that's on the resistor body, you want to make sure not to mix up the resistors. So you want to make sure that once we're done with demonstrating the 100 ohm resistor is working beautifully and that it is restricting the amount of electricity that flows through the LED such that without the resistor, the LED is brighter as shown here. And then with the resistor, the LED is less bright as shown here. Well, what we're going to do next is we're going to replace this with a 1,000 ohm resistor, and this will be even less bright. But before we do, we want to grab our pouch that holds the 100 ohm resistors. These are quarter watt, tiny, okay, quarter watt resistors. And very carefully open the bag. Tedious when you've got big fat fingers like mine. Okay, plastic pouch is now opened, ready for receiving the resistor. We're going to pull this guy out and be sure we put it back into the 100 ohm, 100 omega pouch and not mix it up with anything else. So we'll open up the pouch. Oops, the rest of it comes out. And push that back in and then grab the resistor. Plump, and put it back into the pouch like so. Seal this up. Then and only then will we go to open up our 1K ohm resistor pouch, which I have done. We will go ahead and pull out our 1K ohm resistors like so. We will, as we've done before, hold on to the tape, hold on to one end of the wire, pull that very carefully out of the tape on one end like so, like so. And then do the same on the other end, like so. Set this on the board, take the rest of these, put them back into the pouch. Never leave the resistors out on your desktop without being on your breadboard or in their pouch. So set that aside. And now you want to make sure that there is no sticky residue on either of these ends. So I said that as long as your hands are dry and clean, you should be able to twist off any kind of residue. We call that schmutz off the end of the middle ends, like so. Make sure there's no gummy residue that goes into your tie points. Then we're going to grab the resistor and give it a bend, and give this a bend so it looks like the letter C. We're going to very carefully put this in place where the other resistor was. Push this down into 32E and push this down into 40E, like so. Okay, carefully like so as not to bend the leads, make sure that's firmly in place. Feels like it's pretty solid. And touch the button, light it up. Yes, quite a bit dimmer. In fact, let me take off some of the illumination out here, take off this illumination and light this up. You can see very, very dim in comparison to the 100 ohm resistor. My board is on, my LED is barely lit because 1,000 ohms represents quite a bit more resistance than the 100 ohms by a factor of 10. So if I go to bypass this just for giggles and laughs, because I want to see how bright this LED can be without a resistor, grab my black jumper wire and bypass the resistor by coming all the way over to this end. Wow, that guy is bright right there, very bright. But if I go to hook it back in place with the resistor, the LED is barely on, just barely, right there and right there. All right, excellent. Now we turn this guy off. And what we need to do to dismantle this, if we choose to dismantle this, is to pull off the pieces one by one. But before we do, since this is nicely built, I did recommend that with your rearranged kit box, that you can pre-build your circuits at home, because that's where it's very time consuming for you to arrange things. You can pre-build this at home and take it to school with you and show your instructor how you're progressing, and also do this with testing with the benchtop equipment, which is far more precise than your handheld devices. But how can you transport this without the parts falling off and getting crushed? The way you do that is, as I mentioned to you before, you take your kit and you empty it of the excess stuff. Okay, so this bin is completely empty. I will put in my handy dandy needle nose pliers like so. I will put in a few of these jumper wires because it's handy for me to have them in place. Disconnect my USB cable. USB cable can go down here when you need it. And then the project board can go right here, intact, very nicely. And this bends down just ever so slightly. Your resistor packs and your jumper wires and LEDs are going to be most often used. Put that in like so. Take, fold over. The paper goes in like so. And clip in place. And what did I recommend? I recommended put in a stout rubber band, and you are good to go. Okay, is that wonderful or not? All right, helpful tip. I hope you find that helpful. One more helpful comment from my colleague down under had suggested, and that is, in my enthusiasm of delivering the content, I may have skipped you being able to actually hear the beep of the multimeter during the continuity test. So with that being said, I'm going to demonstrate that right now. I'll just have this part of the board to play with, and we want to demonstrate continuity. So what I'm going to do is I'm going to plug one end into the blue rail here, another end into the blue rail here. This is disconnected from power, so it's completely out of the circuit. We're going to set our multimeter into the continuity test mode. We will take our test leads. Remember, anytime you test anything on the board, you want to make sure your leads are properly working. And we're going to test our test leads first. These have the protective caps. We're going to, for this moment, remove them carefully. And now listen carefully, and I'll try to do it this way so that the microphone can be in a good position so that you can hear the beep. And I'll just shut up so that you can actually hear the beep. And when I go to touch these two together, listen carefully, and the display will change also. Let me see how I can do this. Do this. Okay, ready, set. Hear the nice beep? That shows my test leads have continuity and they're working nicely. This particular nifty multimeter also happens to have a colored bar here that'll light up in addition to the sound. And the display is measuring how many ohms there are, how much resistance is in the wire itself. So that's what the display is showing us. So this is the continuity test mode, the one with the little speaker symbol. The little LCD display screen shows we're in the continuity mode because it's showing the display symbol up there, and touch continuity. Now, we're going to do this on the board also and demonstrate from the underside why we have continuity. And that is if I go to touch here and here, listen carefully. My hands are shaking. There we go. And then if I go to touch here to here, but if I go the one next to it, nothing. Go the one right next to it, nothing. This top rail to either one of these is a nothing. This top rail to the one below it is nothing, but the one below to the one below. Quit shaking here, pal. There, nice. And steady beeps. Now, how do we test it with our jumper wires? With our jumper wires, we'll do it this way. We said to grab a hold of this, squeeze, and remember your hands have to be clean and dry. Go to squeeze the stainless steel pin of the black lead onto this probe. Well, let me switch black to black, be consistent here, squeeze, and then this other end, just simply touch, and we should have continuity through this blue rail. And do we beep? Nice. It beeps. I'm just pressing against the wire. Now, suppose I move this up to the red rail. Should it beep? No. And we don't hear a beep. Suppose I take this and move this anywhere else on the blue rail. Does it beep? Oops, come back here. And touch and hold. This way. Nice. Okay. Continuity. So thank you, dear colleague from Down Under, about that helpful reminder of letting my students actually hear the beep. So I welcome all your comments. And if you like the information you've been introduced so far, please hit the thumbs up, the like button. That helps me to make more videos. And also there's links in our YouTube that will guide you to where you can acquire the recommended multimeter, where you can acquire the recommended project kit, and other things that we will be suggesting from time to time. There's an affiliate link in our YouTube as well. And there's also a Patreon page, a Patreon link, which means that if you'd like to support this channel monetarily with a small donation, that'll help me acquire more equipment for producing these videos, that would be even more wonderful. So keep all those things in mind. I look forward to showing you the next video that when we get together. So until then, cheers and adios from Las Vegas. Have a most blessed day.